storage quota. Today we are going to discuss about Galilean transformation. What are Galilean transformations? Galilean transformations, also called Newtonian transformations, set of equations in classical physics that relate the space and time coordinates of two systems moving at a constant velocity relative to each other. Galilean transformations are used to transform a few physical quantities such as position coordinates, velocity, acceleration, etc. from one inertial frame to another frame of reference. To explain the above facts, let me consider two frames. One is S and another is S dash. S dash is moving with constant velocity v relative to S in such a way that all the axes of frame S dash remain parallel with the axis of frame S. Let me consider an event that is happening at point P. This can be observed by two observers, O and O dash. O observer is in frame S and O dash in frame S dash. Let the coordinates of P in frame S are xyz and in S dash are x dash, y dash and z dash. At t equals to 0, both the origins means observers O and O dash are at the same point. At any time t, the position vector of origin O dash will be O dash equals to Vt. Then in triangle O dash P, according to vectors law, we can say that R dash equals to R minus Vt. This equation is called the Galilean transformation equation of position vector because this is showing the position of the particle in both the frames. Now we can write this Galilean transformation equation in coordinates like x dash equals to x minus vxt, y dash equals to y minus vyt and z dash equals to z minus vzt, where vx, vy and vz are the components of the velocity along the directions. Now we will take transformation of velocity. From the equation of Galilean transformation of position vector, we have r dash equals to r minus vt. Differentiating with respect to t, we get v dash equals to v minus v, where v and v dash are the velocities of particle in frame S and S dash respectively. Now transformation of acceleration. From the Galilean velocity transformation equation, we have v dash equals to v minus v, where v is the velocity of the frame S dash respect to S. Differentiating above equation, we get dv dash upon dt equals to dv upon dt. As we know, v is constant, so dv upon dt equals to 0. So we can say a dash equals to a. Above equation is called Galilean acceleration transformation equation. It is clear that acceleration does not change. In other words, we can say if no force is acting on the particle in one inertial frame, then the force will also be 0 in another inertial frames. Hence, Newton's law of inertia remains valid in all reference frames. We can write transformation of force. From the equation of Galilean transformation for acceleration, we have a dash equals to a. On multiplying both sides with m, we get f dash equals to f. Thus, the force acting on the particle in all inertial frames remains same. This is called law of Galilean invariance of force. Now, law of conservation of momentum. Let we have the masses of two particles are m1 and m2 in frame S, and they are moving with velocities u1 and u2. They collide and after collision they move with velocities v1 and v2 velocities. Then according to the law of conservation of momentum in frame S, we have m1u1 plus m2u2 equals to m1v1 plus m2v2. In frame S dash, the momentum of particles before collision m1u1 plus m1u1 dash, this is m1u1 dash plus m2u2 dash. After collision m1v1 dash plus m2v2 dash. But from Galilean transformation we have u1 equals to u1 dash plus v, u2 equals to u2 dash plus v, v1 equals to v1 dash plus v, and v2 equals to v2 dash plus v. By substituting these values in equation, we get m1 u1 dash plus m2 u2 dash equals to m1 v1 dash plus m2 v2 dash. So we can say that the law of conservation of momentum is invariant in all inertial frames. Now we will see transformation of the displacement between 2 points. Let the position vector of 2 points P and Q and R, R1 and R2 respectively. Here we are having frame S and also S dash. There are 2 points P and Q. The position vector of P in frame S is R1 and position vector of Q in frame S is R2. So the displacement vector between P and Q in frame S is PQ equals to R2 minus R1. From the Galilean transformation, we are having R1 dash equals to R1 minus Vt and also R2 dash equals to R2 minus Vt, where R1 dash and R2 dash are the position vectors of P and Q in frame S dash. Thus, displacement vector in frame S dash equals to R2 dash minus R1 dash. By putting the values of R2 dash and R1 dash, we get R2 minus R1, which is the displacement in frame S. So we can say it is clear that displacement vector between 2 points is invariant under Galilean transformation. This is called law of Galilean invariance of displacement.